Chapter 34, Ray Optics, explores some of the many things that can be explained by regarding light as an infinite number of rays emanating from a source or reflecting off of a surface, being absorbed and re-emitted. There's not too much talk of wave fronts, wavelengths, any of the wave aspects that we looked at in the previous chapter. You cannot use ray optics to explain the spreading of light upon passing through a narrow opening. You cannot use it to explain interference. Those are all wave phenomena. So this chapter is about explaining the bending of light as it passes into a medium where the speed changes. You can explain lenses, mirrors, optical instruments that use lenses and mirrors, including your eyeball. But most of the optical instruments are explored in the next chapter, chapter 35. So wave fronts and rays, they coexist. Remember that we think of these, usually when you draw these circular wave fronts, these circles may represent spherical wave fronts, but the circles themselves are thought of as the peaks on the sine waves, and then the troughs are the dead space in between the wave fronts. So one wavelength is the spacing between these consecutive circular wave fronts. And the rays, they're just straight lines that cut across the wave fronts perpendicularly. That's it. The rays are orthogonal, or lines which are orthogonal to the wave fronts. And that's true even if the wave fronts are not circles. Even if they had a more complicated curvature, the rays would always cross perpendicularly. If you look at the limit of a spherical wavefront, as the radius goes to infinity, eventually those circles start to look like straight lines themselves, but the rays are still perpendicular. And let's switch over to PowerPoint here. Look at some graphics from your book. You can think of a laser beam as a really good approximation of a bundle of rays. They've only drawn a few, but the idea is there's, you can pack an infinite number in there. First, we should look at reflection. It's remarkable how much you can do with one very simple rule, the law of reflection. So we'll look at that in a moment. And as soon as you know the law of reflection, you can explain how an image is formed by a concave mirror, which means you can explain many types of telescopes with just that one simple law. Point source, here's rays emanating from the source. And by the time you've gotten very far from that source, you're so far away that any set of rays coming from that source look as if they're coming in parallel. You'll have to pardon some of the awkward pauses in this video. If I had more time and better software and know-how, I could stick in some elevator music. But as I'm switching back and forth between the camera and screen sharing, there's going to be some awkward pauses. So, go grab a snack. Your book does not do this, but it's not difficult to, actually, I think they do this, but in a different way. I'm going to present to you how to think about the law of reflection using the wave model of light. Here are three representative rays. Remember, they're orthogonal to incoming wave fronts. Imagine these wave fronts have come from some source over in that direction, but it's super far away, which is why these rays are coming in parallel. And they strike the surface of something that's very smooth. Your tabletop might look smooth, but if you could make yourself the size of, a bacterium singular, you would see that there's all kind of bumps. It's not very smooth up close, but a polished mirror is rather smooth, even at that scale, I assume. So here's a perfectly smooth surface, and we know that matter is made out of atoms. So atoms are what? A nanometer apart, a tenth of a nanometer apart. Just imagine a series of tiny little dots here that are very close together on the scale of nanometers. And I should have a better graphic for this, but we know that electromagnetic waves, which is what light is composed of, the electric field will cause electric charges to oscillate. So each of these atoms has electrons buzzing around it. That's one way to think about it. And we know that the electric field will classically, we think of the electric field as causing those charges to oscillate. And what happens when you take a charge and you shake it? It emits its own electromagnetic wave. So imagine all of the dots here, which represent atoms, being forced to jiggle and re-emit their own waves. So I don't want to draw on this because this is my original, but if we had a series of dots, you could imagine circular wave fronts coming out of each of these dots. So you've got all these circular wave fronts moving outwards, and they're going to interfere with each other. This set of three lines represents the rays perpendicular to those reflected wave fronts. So you've got a wave front coming in, and then it causes each of these little atoms, I'll call them, to emit their own circular wave fronts that are moving out in this direction. And we'd like to ask, what type of interference do you get at some arbitrary angle? That's what we're looking at. So I've picked an arbitrary angle coming in and an arbitrary angle going out, and I'd like to investigate whether the interference between those waves is constructive or destructive. So let's just take two of the rays. Now here's a convention that you'll see throughout the semester, and I know that the focus here is not great. I'll be working on improving the lighting here, maybe even the camera. But this line that I've drawn perpendicular to the surface, they call that the normal line. This is the normal line, and almost always we measure angles from the normal. That's very important in this chapter. So I've labeled this incoming angle theta 1. That's the angle of incidence. And I've drawn a different reflected angle. I've called that theta 2. All these angles, or all these rays, are going out at the same angle to the normal. That angle is theta 2. And let's just focus on this ray and its reflection, and then this ray and its reflection. And you'll notice that this ray travels a different distance than this ray. We're going to assume that these two rays represent identical sources. And in fact, they would have come from the same source very far away. So this point on the wave and this point on the wave, they're in phase. They're either going up at the same time or going down at the same time. And down here, at the point where the first ray hits the surface, I have drawn a line perpendicular over to the other ray. So you can see up to this point, these two rays have traveled the same distance. But this second ray is going to have to travel a little bit further to get to the surface. And I've darkened this segment here. So this is the path length difference before the two of them hit the surface. Once they've reflected, if you look at this ray and this ray, I've drawn another perpendicular from here to here. So from this point on, this ray is going to travel the same distance as this ray. So it's actually the first ray coming in that travels this little extra distance on the way out. So let me back up again. On the way in, this ray travels a little extra distance here. On the way out, it's the first ray that travels this extra distance. And I will scan this and put it on canvas so you can take a closer look at it. I'll probably redraw it. So if we're interested in the total path length difference, we'd have to subtract the two, because this is the extra distance that the second ray travels on the way in. From that, we'll subtract the extra distance that the first ray travels on the way out, and that'll give us the total extra distance that the second ray has to travel. And that's what I've done here. Let's look at how I did that. I'm just using right triangles here. So this right triangle, I'm using the letter D, because we've been using D often for the distance between two sources. D is the distance between two of those adjacent atoms, let's call them. And I think I'll let you stare at this for a while and see if you can figure out why this angle right here, let me trace that again. This angle is also theta 1. You could spend some time staring at this and sort that out. And the side that I'm looking at is opposite theta 1. Since D is the hypotenuse, D sine theta 1 would give me the extra distance that the second ray travels on the way into the surface. And I've written that here, right here. The second ray, on its way out, has to travel, I'll just go ahead and darken this right now, has to travel this extra distance. Now I'm looking at a different right triangle. this triangle right here. Trace that one more time. This extra distance is opposite this little angle here. Again, I know the video quality is pretty poor here. You can show that this is theta 2. If you were to take some time looking at this figure, this is theta 2. So since this side is opposite theta 2, it's the same hypotenuse as before. D sine theta 2 would give me the extra distance traveled by the first ray on the way out. So the total path length difference, delta R, would be d sine theta 1 minus d sine theta 2. Now, when I first wrote this down, I just set that equal to 0 because I was thinking about constructive interference. But if you'll recall, the path length difference does not have to be 0. It could be any integer multiple of the wavelength lambda. So down here, you know, I'm going to have to redraw this anyway. So let me just erase this and write m times lambda. The path length difference, whatever it is, needs to be an integer multiple of the wavelength if these outgoing two waves are going to interfere destructively. And you can see, because all the angles are the same, whatever produces constructive interference for this pair of rays or waves will also work for this pair, and then this wave paired with the wave to the right, which I haven't drawn. So it would just continue on down the line. If I rearrange this slightly, I get to this equation, which says that d sine theta 1 would have to equal d sine theta 2 plus lambda times n. And if you look now, this equation can be solved for the particular angle or set of angles, theta 2, at which you would get constructive interference. So no, there's going to be multiple solutions for various values of m. Let me solve for theta 2 in terms of everything else. So I would have to move this to the other side, divide out the d, take the arc sine. And I wind up with this formula, which you can probably barely read. Theta 1 would have to be the arc sine of theta 2 plus this garbage that's got an m in it. Now, let's zoom in on this ratio here. We keep seeing this ratio everywhere. Wavelength compared to the separation between, in this case, the atoms, not slits. Well, the wavelength of visible light is something like 500 nanometers. But if we're imagining the surface of a mirror made of atoms, and maybe you don't know this, but a mirror, I think, is basically a slab of glass with a very polished sheet of metal at the back. So let's just think about the metal. The atoms in that sheet of metal are very close together, something like 1 nanometer apart, maybe even less, not 500 nanometers. So this ratio in this instance is actually much greater than 1. Previously, we were talking about the slit separation d, and we found that this was a number much less than 1. Now we're talking about a wavelength of lambda that's way greater than the spacing between the atoms. And that means the argument of this arc sine function is way bigger than 1. Even if m took on the value of 1, we would be taking the arc sine of something like 500. And there is no real angle that has an arc sine, or there is no real angle for which the sine is something like 500. And that means the only way this works is if we plug in m equals 0. Theta 1 would have to be the arc sine of the sine of 2. In other words, theta 1 has to equal theta 2. All of this to say that you watch these rays come in and reflect. At any arbitrary angle, you would find that the reflected waves are not interfering constructively. They have a phase difference between them due to a path length difference. And in general, that phase difference is not 0 or 2 pi or 4 pi. It's going to be something else. However, there is a particular angle at which these reflected waves do interfere constructively, and that angle is theta 2 equal to theta 1. In other words, and this is where it gets a little difficult to conceptualize, because we know that it doesn't have to be perfect or a maximum constructive interference or perfect destructive interference and nothing in between. You can have anything in between. So presumably, this light would be reflected at all angles. It's just that you would see it most intense in the in the direction that's such that the reflected angle is equal to the incident angle. And as I'm thinking about it right now, I'm realizing, you recall for multiple slit interference, do you remember that the more slits you have, the more concentrated the energy becomes along the direction of interference maxima? Like for two slits, there's quite a bit of intensity even in between the fringes. By the time you get to like 500 slits per millimeter in a diffraction grating, there's almost no light energy in between those maxima. And I think we're looking at the same thing here. If you've got millions of atoms along the surface here, you would get a really sharp distribution of energy so that it's almost completely destructive interference at all angles except for the where the angle of reflection is equal to the angle of incidence. Okay, if you didn't follow all that, it doesn't matter, because as far as solving problems in this chapter, all you have to know is the law of reflection, and that is that the angle of reflection, I'm calling it theta 2, would equal the angle of incidence. And that one concept alone will allow us to do all sorts of things. So I will pause and come back and apply that to explaining how a flat mirror produces an image. First, let's look at the pinhole camera, which does not require the law of reflection. Your book points out that this word camera, I think it's from some Latin word, camera. Even in Italian now, it means like chamber. So chamber music in classical music is called musica di camera. Let's see here. I'm looking at the top of the tree. Okay, trees do not emit their own light. You can't see them in the dark. If they were emitting their own light, they would be on fire. You can see a tree because it's reflecting light that comes from the sky. Direct sunlight or light that's already been scattered by the atmosphere, you can call that skylight, whatever. You can imagine a whole bunch of rays coming out of the top of this tree, and your book makes this exact same argument. They have to be going in all different directions because you can see the tree no matter where you're standing. So there are rays going in all different directions. But let's just look at a representative ray, or a couple representative rays, heading towards the hole in this box. Here's one. This ray would actually make it through the hole, and it would strike the surface at the back of the box. If I drew another ray at a slightly different angle, it gets blocked at the opening and it doesn't make it through. You could repeat this argument all the way down the tree. So if we look at rays emanating from the bottom of the tree, I'll pretend that only one of those rays actually makes it through the hole in the pinhole camera. And it ends up over here. Same thing here. Draw a ray from the middle passing through here, and it would form an image over here. And I think you're getting the idea that what would show up over here is an inverted image of the tree, upside down and reduced in size. And believe it or not, you could produce an image this way. Maybe some of you made a pinhole camera as kids. I don't think I did, but I did do it as an adult. There's tons of YouTube videos. I think I've got some videos on Canvas that will show you some nice pinhole cameras. You could do it with a shoebox and a piece of tissue paper. As long as you're looking at something very bright, you will see a very clear image at the back. It's pretty cool if you've never done it. Since you're stuck at home with the coronavirus, check it out. Get a shoebox and some tissue paper. Let's just look at the simple geometry here. You've got a triangle here and a triangle here, and they're similar triangles. It's been a while since I've done geometry, but how do we know the angles have to be the same? Well, I don't know, alternate interior angles. This angle has to be the same as this angle, same for this pair, and obviously these are the same. So if all the angles are the same, similar triangles, fine. And let's label some things here. We're going to use these letters throughout the chapter. The distance from the so-called object. This is the object, this is the image. The distance from the object to the pinhole, I will call S. That is the object distance. The distance from the pinhole to the image is S prime. That's the image distance. Notice we formed an image, by the way, with no lens. There was no mirror here and no lens. You don't even need either of those to form an image. You just need a hole. And that is how probably the first eyeballs that existed on this earth worked. They were simply, imagine your eye was just a pupil with no curvature. You know, the front of your eye is spherically shaped, so it's got curvature. And then beyond that, you've got an additional lens inside your eyeball, which is really gross to think about. And I've never actually seen the lens of an eye outside of an eyeball. I think that would be disgusting, but it's in there. Even if you just had a membrane, a flat membrane with a hole and some light sensitive cells in the back, like your retina, you could probably see images. There's a great video that I think I put on Canvas with Richard Dawkins talking about as he says, the evolution of the eye. We'll call this distance y, that's the object height, and then this would be y prime, the image height. And then we'll just use proportions. This compared to this should be equal to this compared to this. Or I could also just say S compared to S prime is equal to Y compared to Y prime. If you rearrange this a little bit, you'd have Y prime is equal to S prime over S times Y. And this is how you will often see it later in the chapter when we get to mirrors and lenses, or images formed by mirrors and lenses. It allows you to find the height of the image in terms of the height of the object, and you just need the ratio of the image and object distances. And later we'll see that sometimes this ratio is considered to be a negative number, which means your image height would come out negative, and that tells you that the image is inverted. Pinhole camera. Now let's take a look at what a mirror does. So I will share screen again. We'll take a look at PowerPoint, just some of the images from your book. You'll notice I'm really just following the order of presentation of your book here. You've got this graphic of the law of reflection. Remember, we always measure angles from the normal, so you wouldn't be measuring this angle, you'd be measuring this angle for the incoming ray. And also, the plane, not airplane plane, but like geometry plane, the plane formed by the normal and the incident ray, that's called the plane of incidence, and it's just a fact that the reflected ray also lies within that plane. Because you might imagine, what if the incident ray comes in like this, and then bounces off so that it's coming out of the screen at you? That just doesn't happen. And if you want to know why, you'd have to look to Maxwell's equations. You can use them to show that the reflected ray must be in the plane of incidence. And my computer seems to be stuck here. Here we go. There's a nice practice problem in there about using the law of reflection. I hope you're reading everything in the chapter. They briefly talk about the difference between, irregular reflection, or diffuse reflection, they call it, and specular reflection. We're only concerned with specular reflection. The word root has something to do with mirror, so reflection from a flat surface, smooth surface, that's what we're talking about. You cannot form an image off of a rough surface like this. You can imagine that if you looked at your tabletop up close, it would look more like this than something smooth. That's why you can't see an image of your face in a tabletop, a wooden tabletop. You need something very smooth. Okay. Here's some source of light in front of a mirror, like a light bulb. And look at all the rays coming from the source. Each one of them, when it hits the surface, will bounce off at the same angle. It's a lot like pool, right? If you've played pool, billiards, many of you know that you can expect the pool ball to bounce off the side of the table at the same angle at which it came in. Angle of reflection equals angle of incidence. You can observe that that's true for each of these rays. And that is how the image is formed. If it weren't for the law of reflection, you wouldn't see an image in a mirror. This is the setup that we'll use. Let's see, what can I say here? If theta I equals theta R, the angle of incidence equals angle of reflection, this angle here has to be the same as this angle. I think they call that vertical angles in geometry. And that's how we know that this angle is the same as this angle. So I'm going to do that on paper now, and we'll show that the image point is the same distance behind the mirror that the object is in front of the mirror. So let me turn off the screen share here. Oops. Stop share. Okay, and now we'll draw a picture here. Here's the mirror. Let's look at a source of light right here. This is the object distance S. And again, this could be a light bulb. It could also just be like your nose. It could be a particular point on your face, and there's a bunch of rays coming out of your nose. Well, not out of your nose. That sounds, you know what I mean. Light rays bouncing off the surface of your nose. And I'm going to look at two of those rays. One of them, you can imagine striking the mirror like this. Now, what is the angle between this ray and the normal? Actually, this ray is along the normal, so that angle is 0. It's just going to bounce back right where it came from. So that ray is going to be reflected backwards. Now, if your eyeball is over here, and I'm not going to draw it yet, but that's a little weird to think, because if this is your nose, your eyeball would be up here, right? So again, let's just pretend I'm talking about a light bulb. And I'll draw a different ray now. Now, how do I decide which direction this thing's going to bounce off at? I know it's got to bounce off at the same angle at which it came in. So I will draw the normal first. I like to do a dotted line. That came out pretty good because these look parallel. Now, if you were trying to draw a precise ray diagram, you'd want to use a protractor and make sure that the angle is the same. I'm just going to eyeball it. This looks good enough. This reflected ray goes off in this direction. Okay. Now, this is going to seem a little weird, but I'm going to draw a giant eyeball right here. Here's your pupil. Gross. Just imagine that your eye is collecting both of these rays. They're going to be bent at the surface of your eye, and focused at some point behind where your retina is. But your brain has no idea necessarily. Well, let me back up here. We all know what a mirror is, but if you were born yesterday and you didn't know what a mirror was, your brain has no idea of knowing, or no way of knowing, that this ray had been reflected off of a surface, that the ray had actually come from over here. As far as your brain is concerned, this ray came from somewhere back here. So I'm going to extend this ray backwards. And you may think I'm being a little pedantic here, going into too much detail with this rather simple topic that was presented in your book, but you do want to think about this carefully, because it gets more complicated when we get to lenses and mirrors. Same thing with this ray. Your brain perceives this light ray as if it's come from back here. And you'll notice that if we extend these two rays backwards, they appear to be coming from the same point. So as far as your brain is concerned, maybe it's a little odd to talk about your brain as if it's separate from you, but that's metaphysics. I don't know anything about that. It would appear that the so-called image point, if we call the object point P and the image point is P prime, it would appear that P prime is the same distance behind the mirror as the actual point is in front of the mirror. And I could repeat this with a whole bunch of rays. I've only drawn two. Let's just do one more to get a sense of what's going on here. Here's a third ray that I'll draw off in this direction. Let me draw the normal so that I can enforce the law of reflection. And here's where I want to be careful, because if I'm not careful, these three are not going to actually cross through a single point. I'll cheat. I'll put the ruler so that it goes through the image point. All right, so if I extend this backwards, yes, oh, what a surprise. It does go through the image point. All right, pretty cool, right? All of the rays coming out of this point reflect in such a way that they appear to be coming from a single point on the other side. That's the image point. And it's very important to understand this, or to learn this term now. This is called a virtual image, because there are not actually any rays coming from this point. Presumably, this is a solid mirror and there's no light going back here. So if you stuck your eyeball right here, if your eye was here looking that way, this way. You wouldn't see anything. The rays only exist over here. The light energy only exists over here. In that sense, it's a virtual image. Later, we're going to look at real images where you could put a piece of photographic film here and actually develop an image. So sometimes the rays actually would be converging and there is real light energy there. This is a virtual image, not a real image. Okay, we could do some geometry real quick just to confirm that this distance is the same as this distance. How do we do that? Well, this side is congruent to itself. Fine. I'm looking at this right triangle and this right triangle, and I want to show that those two triangles are congruent. Okay, so if this is theta incident for I'm looking at this ray right here. If this is theta incident, well, the reflected angle has to be the same, so that's the same as theta incident. I'm just calling it theta 1. This must also be theta 1. Fine. Okay, well, doesn't this angle and this angle, don't they add up to 90? So this would be 90 minus theta 1. Of course, this is also 90 minus theta 1. I think you see that this angle is the same as this angle. So we've already got a side in common and an angle in common. I think we can use angle, side angle. Well, we've got it already because remember, this is normally incident. So 90 degrees, 90 degrees. There we go. These two triangles have an angle, a side, and an angle in common. They must be the congruent triangles, so we know that this side has the same length as that side. And now we've established that if you're standing 5 feet from a mirror, you see an image of yourself. It looks like your doppelganger, your identical twin. How far does your identical twin appear to be standing on the other side of the mirror? If you're 5 feet in front of the mirror, your doppelganger appears to be 5 feet on the other side of the mirror. In other words, they appear to be 10 feet in front of you. I think I did that right. 5 plus 5 equals 10. I think I will end this video now. That's enough to say for now about the law of reflection. I'll come back with another short video and apply wave interference to the concept of refraction. As light goes from, for instance, air into water, we know that it bends, and that can be explained using the wave nature of light. That's called Snell's law. And like I said, your book does interpret Snell's law from the perspective of the wave model for light, but they do it in, to me, a somewhat unsatisfying way. So I will look at that in the next video. And as soon as we've got those two results, the law of reflection and Snell's law for refraction, we're off to the races, because we can explain how light behaves as it goes from air into a chunk of glass that's got a spherical surface. And as soon as we've done that, we can put two spherical surfaces together, squash them together. That's called a lens. And we can explain how a lens works. And you'd be surprised how many things you can understand after you've looked at the optics of a simple thin lens.